recap of the last session, and this is where we started. Milestone 1. The name of milestone 1 is Apache Spark. Got it? So do not think that these lectures are not relevant to the Spark module. This is Apache Spark. But in order to reach the Apache Spark, we need to have these ideas with us. Otherwise, our understanding of Apache Spark would be incomplete. Okay. Uh, this was session 2. In session 1, we saw Hadoop from storage point of view, and we discussed HDFS, and we saw how a file is split, the blocks are created, and the blocks are stored. We saw what is the default block size. We saw whether we can change the default block size, we can increase or we can decrease. We saw what are the advantages and what are the disadvantages of increasing or decreasing the block size. And I told you very important thing, that 128 MB is not a divine number, but this number comes from some experience, that this is the stage which we can afford. Got it? So after that, yes, I told you that HDFS is a data lake, and this data lake is in the Hadoop ecosystem. So what are the alternatives of HDFS, Hadoop distributed file system? What are its alternative in the cloud? So in cloud, we have Amazon cloud, we have S3. In Azure cloud, we have ADLS Gen 2. Okay. So after that, we discussed what are the differences between HDFS and data lakes. HDFS, which is a data lake, but in the Hadoop ecosystem or in the Hadoop architecture, and what are the differences between HDFS and data lakes on the cloud. So first of all, I told you that HDFS is not persistent, but S3 and ADLS Gen 2 or any cloud, any data lake which comes in the cloud are persistent. And what do we actually mean by the persistent? We mean by the persistent that when we shut down the cluster, when the cluster is shut down, the data is lost. In what case? In HDFS case. Got it? When we, I repeat, when we shut down the cluster, or when by any disaster or by any unexpected reason, when the cluster is shut down, the data is lost. But this is not the case in any cloud. In any cloud data lake, for example, if you store an employees table in Amazon S3, it would remain saved for an infinite number of time, or for an infinite time, or for the time when till when you wish to keep it saved. Got it? If the cluster is shut down, the data remains the same, or the data remains intact. But if but in the case of HDFS, when you shut down the cluster, the data is not saved. We will see this property in Databricks also, when we come to Databricks, and when we come to Amazon cloud, or when we come to Azure cloud. Okay, then the next drawback is that compute is data is coupled with compute. Yes, storage is tightly coupled with compute. What do we actually mean? That, look, for many reasons, we might have the requirement that we only need to save the data. So generally, we should only get the storage and not the compute. But when we order such thing in the Hadoop, for example, if we wish to save 3 GB file in HDFS, we would get two things. We would unwillingly get two things. The first thing is the storage, and the second thing is the compute. This is not the case that when we order only storage and we get only storage. No, when we order storage, we would get compute also. So ultimately, we will have to pay for both. So this is not a favorable thing. I mean, generally, If I need to only store 3 GB file for 1 year, so I have to pay for only storage. Why do I have to pay for the compute also? And generally, storage is very cheap. You can store GBs of data in Amazon S3 for free in a free version. This means that you're storing for free. Not totally free, but you get some credits, but that is ultimately free for you. But compute is very costly. So, for example, if data storing cost you $3 for 1 month, the compute would generally, I'm not giving a very exact number, but I'm giving some exaggerated number. If the storage is costing you $3 per month, the same compute would, or it might cost you $30. So just for the sake of $3, would you be willing to pay $33 or $30? No. So this is another issue with HDFS or Hadoop storage. But S3 and ADLS Gen 2 are persistent. The data is not lost when the cluster is shut down. They have different layers, stuff like that. All right. I hope this is clear. This was just a quick review of a quick recap of these things. There was one more thing I wanted to tell you about these this HDFS and S3. Yes, yes. HDFS is a, let me just HDFS is a file system, but they are object stores. And this is a kind of assignment for you, that you have to read about the differences between a file system and object stores. I'm giving you this as an assignment. I will be asking you the same in the next session, that what is the difference between a file system and the object stores. All right. After that, we studied getting started with the distributed compute. In our example, we had a 4-node Hadoop cluster. By 4-node, we have 4 slave nodes or 4 worker nodes or 4 data nodes. This was the file, and we needed to count the frequency of each words. We need to count for how many times hello is coming, for how many times teach is coming, and for now how many times data is coming, and all these words. Okay, so I told you that when we need to process this file in MapReduce, this is a two-way activity. Sorry, two-phase activity, not a two-way activity. This is a two-phase activity. The first phase is mapping, and the second phase is reducing. Mapping, what it does, it prepares the data for aggregation, and reducing, what it does, it actually performs the aggregation. So we write two codes, first for mapper and the second for reducer. And then I told you the code goes to data, not the data goes to the code. How does the code go to the data? For example, this is the code. We have written the code here, and this arrow shows that the code is going to the data. The same code goes to the data node 1, the same code goes to the data node 2, the same code goes to the data node 3, the same code goes to the data node 4. This is not the case that you have written a code for mapper, and one piece of code goes here, the second piece of code goes here, the third piece goes here, and the fourth piece of code goes here. No, the complete code goes into this machine, the complete code lands into this machine, the complete code lands into this machine, and the complete code lands into this machine. And after that, when this activity is happening, or when the code is running in this machine, or when the processing is happening, we say that a mapper is running. We say that a mapper is running. So this is a very important thing, that when we say that a mapper is running, this means that the code is being processed on that node. All right. And two more things to consider. What is parallelism? Parallelism is how many how many processes we can run at the same time. Got it? And this purely depends upon the nodes that are available. If we have 4 nodes, the parallelism is 4. This means that at time t1 we can run 4 processes at the same time. Got it? And the number of mappers, how many mappers would be eventually, how many mappers would run, depends upon the blocks of the file. If we have 8 blocks, we will be having 8 mappers running. And what do we mean by mappers running? The code would go to the data node and the code would process the data. So for 8 blocks we would be having 8 mappers, but how many mappers would run at first? This depends upon the parallelism, and parallelism depends upon the number of nodes we have. If we have 4 blocks, we would if we have 4 data nodes, we would be having the parallelism of 4. So if we have 8 blocks, we will be having 8 mappers. So according to the configuration of this cluster, first process 1 to process 4 would run, and we will say that 4 mappers have run. Once these mappers have completed, then the next 4 mappers would run. I hope this makes sense. So this is parallelism, how many tasks can run at the same time, t1 to t4. Parallelism is always equal to the nodes of the cluster, and mappers are equal to the blocks of the file. If we have 8 data nodes, it means we have the parallelism of 8, and at the same time or at one time we can run 8 processes in parallel. Then I told you that, for example, this is the file and we need to calculate the frequency. This is a very high level view. Now we will see that how these words would be processed at these or each respective node. For example, this is the file 1. This has 4 lines. So we suppose that this is a 500 MBs file. We suppose that this is a 500 MBs file. So according to the default block size, we have 4 blocks: block 1, block 2, block 3, and block 4. So each block has been saved in a single node: data node 1, data node 2, data node 3, and data node 4. Okay, now this file has been saved in a distributed manner. We have written a code. We have written 2 codes. The first code is thrown to the mappers. These are called mappers also in MapReduce paradigm. These are called mappers. The same code would run on each mapper, and they would give their respective output result. For example, this mapper gives the result as R1, this gives us R2, this gives us R3, and this gives us R4. Now is the time that, and let me reveal one more thing, that the output of these mappers is an intermediate outcome. So in order to get the final outcome, this data is generally moved. This is literally moved to another machine that is called reducer. And for this reducer, we have written one more code, and that code would tell that how would this result be aggregated, and this would give us the final outcome. This would give us the final outcome. So this was all we studied in the last lecture. Anybody having any confusion till now? We would actually see how this file would be processed, and we need to find the frequency of each word. So now this file, and we need to count the frequency of each word. This is the file, and what is our assignment? That we need to count the frequency of each word. And what do we actually mean by the frequency of each word? Now I want to count for how many times hello came or hello appeared in this file, for how many times I appeared, for how many times teach appear and for how many times concepts appear, and the same goes for the all the words. Okay, if this is the file and I have told you that the file has been saved in this manner, the first line has been saved in data node 1, the second file has been saved in the second line has been saved in data node 2, data node 3, and data node 4. Okay, and we are assuming that this file is of 500 MBs, and according to the default block size, this would create 4 blocks. This would create 4 blocks. So this file is saved on this partition. Sorry, I will not use the word partition right now because that is specific to Apache Spark. This part is saved on block 1. This is saved on block 2. This is saved on block 3, and this is saved on block 4. Okay, now we will actually see what would happen on each block. What would happen on block 1? What would happen on block 2? What would happen on block 3? What would happen on block 4? Now you are literally going to see how the data would be processed in a distributed manner. Look, if this is the, for example, if we need to count the frequency of each word, and this file is not stored in a distributed manner, for example, this file is saved on our system. This file is saved on our system. Let me just give this here. For example, if this file is saved on our local single machine, this is the file. Now let's just get rid of those blocks. Okay, if this is saved on, and assume this is a table, and if we need to write a and the name of this file is file1.txt. So if I need to count the frequency of each word, what would I say? If, for example, I'm processing this in a SQL kind of syntax, so I would say select count count of words. For example, count of words from file1.txt and group by words. So this would give me a count of each word. Got it? This would give me hello comma 1, I comma 2, since I is being I is appearing 2 times, teach comma 1, big comma 1, 2, 3, 4, 5. So think from a SQL kind of view. So if this file is saved on a single machine, then SQL would work. SQL would work. But note one thing, MapReduce is a programming paradigm, and this could appear in your interviews also. What do we actually mean when we say MapReduce is a programming paradigm? This means that when the data is stored on in a distributed manner, our traditional codes like C, Java, Python do not work. I've skipped Java. C, Python, or C++, let's say, they do not work. We need a specific kind of programming paradigm or a programming framework that make us able to process the file when this file is saved in this manner. So for that reason, MapReduce came, and it came as a programming paradigm that it solved our pain point, that it had specific programming which would serve this purpose, that when the data is stored in a distributed manner or in a on or the data is stored in more than one machines, it would work. So I hope this is clear. Okay, now let's just begin with this. Okay. Note very important thing, both mappers and reducers accept only key value pairs. They both accept only key value pairs. For example, if this is a mapper, it takes input as a KV pair, and it gives output as a key value pair. This is very important property of these both mappers and reducers. Mapper takes input as a key value pair, and it gives output as a key value pair, which is ultimately acceptable by the reducer. So if the reducer accepts only key value pair, it is automatically being prepared by the mapper. But let's take this file, or let's take this line, which is stored on block 1. Is it a key value pair? How would a key value pair look like? Key value pair look like, for example, here we have key, and in the next place we have value. For example, consider a JSON file. We would be having 1 Hamza. We would be having 2,
like dictionary in Python.
not strictly, but like
लाइक अगर
again,
से क्लास भी तो कह सकते
confuse ourselves by using the technical words here. Just do with this a key value pair.
हैं।
The first
ठीक
place would be a key, and the second place would be a value for that. That's it. Got it? I could have used the technical words here, but those would make you confuse. Those would just lead you to some other. For example, if you say a class, it would just take you to the C or Python etc. So I don't want that. Okay. So mapper and reducer accept only a key value pair. Is this line a key value pair? This is only the value. Is it having any key? No. Got it? This does not have a key. Then comes the purpose of a record reader. There is one thing in the MapReduce only, and that is the record reader. What is the record reader? It converts the input into a key KV pair. Okay, KV pair, and which is then acceptable for the mapper. And what would it do? It would do something like that. It would do something like that. And now we are seeing the record reader here. Okay, record reader doing its activity. I'm removing it. I'm packing it inside a bracket, and I'm, for example, it would MapReduce would give a random key to it. For example, this gives 4, 5, 6, 7, and something like that. This is the key for it. like that. But for our simplicity, let's say this has given 0 as a key to it. 0 comma value. 0 is the key, this is the value. This would happen at data node 1. This would happen at data node 1. For this, and suppose the data node 1 have 10 million records, then this would generate 10 million keys for these 10 million values, and this would repeat it repeat itself. This would repeat itself for example 10 million times. This kind of structure would be happening at data node 1 or for the block 1. So I hope this is clear. What would happen at block 2? It's better if I write it here. At block 1, this is the key and this is the value. At block 2, 1 comma, this is the value for it, and this is the key for it. Let me make it more visible, and let me give you some space in order to enhance the visibility. So this is what the record reader has done. Record reader has associated a key for the first line, the key for the second line, the key for the 3 comma this. Hope this is clear. So, and what output we got? We got the output as this. This is a simple line which does not have any key. So the record reader has associated a random key with it. For our simplicity, we used a sequence so that you can understand. Is it clear? And for this is same for the other lines. For example, this and this has been converted to this kind of structure. I copied from here. I'm spending some time here so that you can engage yourself in this thought process, that what is happening in a distributed manner. And this would happen. So the records are sitting in block 1, block 2, block 3, block 4. Since it is our compulsion that mapper and reducer accept only key value pairs, so there is a framework called record reader, and it converts the input into a key value pair so that this input is acceptable for mapper to do the initial activity. So if this is the line, this would be looking like this when the mapper activity is happening. So when I say that mapper activity is happening, what is the very first task which is being done? This is the very first task which is being done by the record reader. Okay, now our data is fully prepared so that the mapper can accept this data, so that this line, hello, I teach big data, can be processed here. So that big data is very powerful, this line can be processed on data node 2, so that I love big data concepts can be processed here, and same goes for this. So is it clear, participants? What is our purpose? The purpose is that we need to count the frequency of each word. Frequency of each word. Okay. Frequency of each word. Now, how would this happen on block 1? Now, mapper activity will happen. At block 1, what do we have to actually have to do? We have to count for how many times hello came, for how many times I came, for how many times teach came. So now since this input is acceptable for mapper, this will come into mapper, For example, I'll say add block, I will say not block, I will say data node 1. Add data node 1. What is the input? Input is this. Okay, this is the input. What would be the output? Output would be, sorry, output would be like something this. Hello, I teach big data. So this is all happening at data node 1. Now, according to our code, I'm not say that exactly this would happen, but I'm just giving you a replication. I'm just giving you an idea that what would happen. The mapper would associate, for example, hello comma 1, I comma 1. For example, what is a mapper code? We say that mapper activity. What is a mapper code? I'm writing a mapper code. I'm just writing the code in a plain English. Associate 1 with each record. Okay. So it keeps on associating 1 with each record. Teach comma 1. Yes. If you have any question, please go ahead. Or block 1. Okay. At data node 2, what would happen? At data node 2, what do we have here? We have this kind of structure here. Okay. So this would be here. This would be here, be here. So at data node 2, look, the same code is being applied. Associate 1 with each record. Okay. Let's repeat this process for data node 3 and 4. So this is the input at data node 3, and this kind of output we are getting. So let me just take a screenshot from any of this output. Look, this was the line we got at data node 1, and this was converted into a key value pair by the record reader, and this is the result 1. I'm pasting it right in front of result 1 so that you can understand. And this would literally happen. This is not something a very visual example. This would literally happen. Okay. At data node 4. At data node 4,
Sir, I am.
which would happen at data node 1, data node 2. Let me just take a screenshot of this as well. R2. This is the output at R3 while learning. Okay. Now we have got 4 intermediate outputs. These are the 4 intermediate outputs. And what kind of outputs are there? These are key value pairs. Now these all outputs would move. Till now the data has not moved. Till now the principle of data locality is being observed. I told you that mappers follow the principle of data locality, and mappers are those which give us parallelism, because reducer is a single machine. It will not give us the parallelism. What gives us the parallelism is the mappers. Now this output would move here, 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 and here. And this process is called shuffle. So I'm just writing a sequence here. What is the sequence? At first, we have record reader. Then what we have? We have mapper. After that, we have shuffle. Okay, a new keyword here, shuffle. What is shuffle? The data actually moves from these machines to another machine, which is a reducer. And in the previous session, I told you this is not another machine, this is any of these machines. For example, data node 3. So all of these results would literally move to data node 3. So when the data is actually moving, this kind of thing, this is called shuffle. What do we call it? We call it shuffle. So I'm writing this shuffle when the data moves among the nodes to reducer node. Okay. So we have understood till here. Shuffle would happen, and what would happen after the shuffle? After the shuffle, we would be having all outputs saved like this. First output, second output, second output, let's not segregate it. Third output and the okay. So this is what has happened after the shuffle. When the shuffle has happened, all the data or all the outputs have accumulated at a single machine. After that, now we have to count the frequency of each word, then sorting would happen. Look, hello comma 1, is this the final output? No, this is not the final output. I'm writing it here. Mapper's output is intermediate output. Okay, mapper's output is the intermediate output. Okay, so we would be having something like that in the initial stages at the reducer. Then sorting would happen. And what is the purpose of sorting? In order to get the final outcome, let me show you how would this happen. Okay, now sorting. When sorting happens, we would be having something like this. Now count. Now the reducer code would come into action. And what is the reducer code? The reducer machine. What is the code? I will say count the number. No, not count. Sum the number of values. What are the values? These are the values. We need to sum. Got it? Okay. Sum the number of values for each distinct key. So for each distinct key, first all the keys would come together. So this is the sorting. We have hello one time. Okay, so hello would come only one time. Okay, or only once. Okay, after that we have the word as I is coming for one time, so I'll paste it here. Sorry, what have I done? I'm just picking the data from the output 1. Okay, I comma 1, just remove it from here. After that we would search that is I coming some other time. So yes, in the output 3 the I is coming for one more time, so I will pick that I'm just let me just I'm literally copying and pasting these records. So this have been copied, this also have been copied, and I have pasted both of them. Now I will search for another I. This is I comma 1. I would cut it, I would paste it. Okay, so we are arrange the same keys together. Okay, we have arranged hello comma 1 together and I comma 1 together. After that I would search for teach, this word. Okay, is it coming? Teach. Okay, teach, teach, teach. No, teach is coming for one time. This would literally happen. ऐसा नहीं है कि ये बिल्कुल ही कोई स्पेक्युलेटिव एग्जांपल है. नो, दिस वुड बी हैपनिंग at each node. When you run the Spark code, these kind of things happen. Okay, teach. Now is the turn for big. I'm picking this word, I'm picking it, I'm pasting it here. Big comma 1. So big is also here. I'm picking it from here, pasting it here. Okay, then I would search again for the big. Yes, big is here. I would paste it here. Then we have, yes, big is here. I would paste it here. And I would go again for the big. I would paste it here. This would, let me repeat, this would literally happen. This would happen. Okay. After that, now is the turn for data. I would pick it from here and I would paste it. Data. Yes, here is one more time. I'm going again to search for it. Spark execution engine would do the same thing internally, but in a very quick fashion. The word data is coming for one more times. I will arrange it here. And I would see that the word data is not coming. Okay. Now you can see that block 1 is disappeared. Now is the turn for word is. I would paste it here. Is the word is coming any more times? No. Now is the turn for very. I'll paste it here. Hadoop. Thank you, MapReduce. Powerful. Okay, after that, the word love. I would paste it here. After that, I'm literally tired of it here. And thank God I do not have to process 25 million records. These are only a few number of records, and this has just given me an extreme tough time. Okay, so after the shuffle, this is after the sorting. Now you can see we have sorted these records. Now what in the next stage, what would happen? This would come together here. and this is 1 2 3 4 times. I'll cut it. One, 2, 3, 4, 5. Let's remove those. Data is coming for 4 times. I'm just get rid out of it. Get rid of those is very no. Let's keep this segregation. So I hope you can understand. This kind of scenario would be present at the reducer. Now what we have to do? We just have to count the values. Count the values. So what output would this give? This would give me hello. I would copy the same. Hello, comma 1. What would this give me? This would give me, what is the logic for this? Sum the number of values. Sum the number of values. 1 plus 1. What is this? This is 2. So this is the output for this. Sorry. For this, do not get bored because I'm not getting, although I'm getting tired, but I'm not getting bored. Okay. For now is the turn for this is I comma 2. This is teach comma 1. This tells that hello came for 1 time, I came for 2 times, teach came for 1 times. For how many times big came? Big came for 1, 2, 3, 4, 5. So I'll pick it from here. Big comma 5. Data comma 1, 2, 3, 4. Data comma 4. Let's assume this is the output of ours. Let's ignore these. I'm not skipping, but I'm just ignoring for saving some time. So what output do we have for this file? For this file, what output do we have? We have hello comma 1. This is the output. I'm just input file. What is the output? Output hello comma 1, I comma 2, big comma 5, and data comma 4. So look, this was the input and this is the output. So we have traveled a lot. So let me now just complete this process. Record reader, mapper, shuffle, then what? Sort, and then what? Reduce. This is the whole scenario coming into picture when any file is sent for processing in a MapReduce program. So this follows this flow. First of all, a record reader comes into picture. It associates keys with each record, and that key value pair is ultimately acceptable for the mapper. These mappers accept the key value pairs which were prepared by the record reader and process them. And these mappers give us the output as key value pairs which are acceptable for the reducer. But before reducing activity, there are two activities which happen. shuffle and sort. Shuffle activity is extremely important because in this we literally deviate from the principle of data locality. We literally deviate from the principle of data locality. What is the principle of data locality? The principle of data locality is that the data is processed on the same machine where it is present. But is this file, or is, when it comes to the reducer, is it being processed on the data node 1? No. Now data node 3 is acting as a reducer. So the file or the records which were previously present at block 1 or data node 1 are now being processed on a alien block or a foreign block or some other block. So this is not local. Got it? So this is the deviation from here. We follow the deviation from the principle of data locality. So once the data sits here, it is then sorted for the sake of aggregation. And after that, when the data is prepared in this fashion, the reducing happens. There is one more thing I could tell you. This would, after that, this is not the output. There is one more thing here. This would also be a key value pair, comma, this bracket, and 1, comma 1, comma 1, comma 1. 1, 2, 3, 4, 5. Okay, let me put one more one here. Now this would be summed. Got it? The same goes for this, the same goes for this, the same goes for these also. So I hope now you have understood a complete picture out of it. Complete picture that once a file is sent to the MapReduce paradigm to be processed, then that file is being processed in this fashion. I hope this is clear. Is anybody? I plan to show you 2 examples, but one example took a lot of time. Let's see. I'm not going to solve it completely. I'm just giving you a reflection of it. This is a CSV file. Suppose this is a 20 records CSV file. I will say orders underscore CSV. Okay. This is the file. And what we need to do, we need to find, let's say, a SQL kind of question. Find each category of orders. इसका SQL किस तरह का होगा? I would say select count of orders. Sorry, if I were to give it a header, the first line is order underscore ID. The second is, this is the second thing, which is a timestamp. This is order underscore date. The third is this is order ID, order date. Let's say this is okay, customer ID and order status. In each status of orders, we want to count how many are the closed orders, how many are the orders which have pending payment, how many orders have been completed, how many are in the processing stage, how many have the pending payment. Got it? So these are all kinds of orders. So we need to count the number of orders in each category. So we would write count of orders from orders underscore CSV group by order status, and I would write the same here, and this SQL would give me some tabular result. This would tell me closed comma, for example, this gives me closed comma. Let's count how many are the close orders. 1, 2, 3, 4. Closed comma 4. How many have pending payment? 1. Let's just quickly go through it. 5, 6. So pending payment 6, closed comma 4. So this kind of result we would get, but this would be very simple when we are solving this in MySQL or SQL Server Management Studio, because they follow a monolithic architecture. They are at a very high level. They are able to process the data when the data is storing in a single machine. But consider a case where it has 4 partitions or 4 blocks. This is block 1, block 2, block 3, and block 4. This is block 4, block 3, block 2, and block 1. So when we need to count the number of orders, first the record header will come and it would associate 0 comma this and make it a key value pair. I hope you get it. Make it a key value pair. It would make this a key value pair, this as a key value pair, and the same process would be repeating on each node. After that, mapper would accept this and it would use only the columns which are useful for our result. We need to count the orders in each category. So it would just go and it would just do what would it do? It would do something like that. Closed comma 1. It will use only these things because according to our query or according to our code, these are the only things which are usable. Other things, order date, customer ID, are not useful according to this requirement. Close comma 1, pending payment stuff. At each node this activity would happen, but if this data is on the single machine, that this would have been the final output. But since these kind of processes being repeated on the other machines, so the result of one machine is not a final output. That is the reason for which we shuffle the data. After shuffling, we would be arranging the keys. We would be arranging closed orders in the same at the same place, just like this. We have arranged big at the one place. We have arranged data at one place. We have arranged I at one place. So we would be arranging. I'm just giving you a complete picture here so that when you approach this picture in a MapReduce style, you would get a clear idea. Close comma 1, close comma 1, close comma 1, stuff like that. Pending payment comma 1, pending payment comma 1, and pending payment comma 1. So this kind of stuff would happen. This kind of activity would actually happen at last, and after that we will just count 1, 2, 3, 4, and we would get the final output as please be comma 4. So just have a look at the output I give you. I close comma 4. So we have reached the same output. This output is for the single machine. This output is for the distributed machines or multiple machines. So this is how the data is processed in a distributed manner. So in the next class, I would encourage any of you to present something that how activity happen I would want you to give me a complete picture of how would this flow look like at block one. This kind of structure would happen. This kind of activity will be happening. Then after that, we will be having this kind of thing. Then after that, we will be having shuffle. Then we will be having sort, and then we'll be having